Okay. I just turned on a fan that creates angular velocity. Okay. How many of you drove to school? Wheels, angular velocity. Okay. Usually when the lights are on, the fan up above here, angular velocity. Angular velocity on the clock, angular velocity on the clock. Okay. Inside the projector, there's a fan, angular velocity. Inside this, there's a fan, angular velocity. Inside the computer, there's some angular velocity. If you don't have a fan inside your computer, it's going to get too hot. Okay? Angular velocity is all around us, and that's one thing we're going to talk about today. Okay? So, before we get into that, I want to go back through the formula we had the other day. S equals r theta. Okay? That is the main formula for finding the length of an arc. S stands for the length of the arc. Okay? The kicker on this is this has to be in radians. Like if I give you 60 degrees, you cannot just plug 60 into that formula. You've got to convert it to radians first and then plug it in. Okay? So, an example. If they said find the length of the arc intercepted by a central angle of 2.5 radians in a circle of radius 5 centimeters. Okay? So we're finding the length of the arc. So we're solving for S. So write the formula down. S equals r theta. They gave us the radius, 5, and this is in centimeters, times the angle. The angle was 2.5, and that's in radians. Put the units on there. Now, the little kicker to this is you can't just multiply that and get the answer and your units are centimeter radians. Is there anything that's a centimeter radian? No. The little trick to this is every time, because of the way we defined that, we defined it a radian to be the length of this radius and the length of this arc were the same, and then this angle was 1 radian. Okay, it's always defined by the radius. So the little trick to this, to get this to work, is to divide by 1 radian. The radius of the circle is 5 centimeters per 1 radian. Then when you put your angle in there, 2.5 radians, then it divides out. The radians divide out, they will reduce. Okay, and if you multiply that out, you end up with 12.5. And the units that are left are centimeters. Okay? Okay, now, I said it. You need to make a note out at the side. The little trick to this, and then some other formulas coming up. The little trick to this is every time you're putting in a radius, it's per. The per is that division line. 5 centimeters per 1 radian. Divide, you have to divide by 1 radian. So always put in the radius per 1 radian. And you are going to work with the units, so you need to put those units in there. Okay? Okay, so that's a little bit of what we did on that formula yesterday. Okay, now the author goes through angular velocity. Angular velocity is angular displacement per unit of time of an object in rotary motion. Okay, it's how fast does that go around? How fast does it go around per unit of time? If it might be in revolutions per minute, it might be in radians per second, it might be in degrees per hour. It's what angle does it map out per unit of time. The formula for angular velocity, it's represented by omega. Looks like a W, don't call it a W. It's omega equals theta over time. Okay? Ooh, hang on. Okay, so on the formula for angular velocity, okay, is omega. So angular velocity is the omega. Theta is the angle, and t is the time. So that's the main formula for angular velocity. Okay, and on this one, the omega is angular velocity. The theta is the angle. It might be radians, it might be revolutions, it might be degrees. Okay, it's an angle per unit of time. And the t is time. And again, the time might be in hours, might be in minutes, might be in seconds. It has to be per unit of time. Okay. In the book, when they use and they tell you something is in RPMs, this R stands for revolutions. This is revolutions per minute. Okay, when you see that in the book. Okay, so let's look at an example. Okay, say they give you find the angular velocity omega. And now when you're doing these problems, I know a lot of people like to write their fractions with a nice diagonal line. Don't do that. Do it horizontally. Okay, everything horizontal, because for the reducing it'll make it much easier. Okay, omega in radians per second for a wheel turning at 40 RPMs. That didn't look very good. So it's going at 40 revolutions per minute. Okay, now this is one of the kind of a weird problem in they're asking for angular velocity, find the angular velocity. And they give you angular velocity. They're giving you 40 RPMs. They're giving you revolutions per minute, and they're asking for radians per second. So all of this is still by formula. Omega equals theta over time. I don't care if you go across or if you go down, there ought to be an equal sign. If you go across, I put in, they're giving us 40, and that's actually revolutions per minute, and they want it in radians per second. Okay, now, to convert it, you've got to have things divide out. And basically, you want the minutes to divide out, and you want to go to seconds. So to get those minutes to divide out, you have to put it up on the top in the numerator, and it's got to be equivalent to the 1 minute is how many seconds? 60, so put that in the denominator. Okay, we want the revolutions to divide out because we want it in radians. Okay, so to get the revolutions to divide out, Put that in the denominator. 1 revolution, and then remember what we did yesterday. 1 revolution all the way around once is how many radians? 2 pi. Okay, so 2 pi, and that's in radians. Write down the units. Okay. Okay, and now you've got it all. Reduce it. Okay, your reducing may not be identical to mine, but the final answer should agree. Okay, so the minutes would divide out. Don't say they cancel. Say they reduce or they divide out. The revolutions would divide out. Okay, you can reduce the 40 and the 60. 20 would go in there twice. 20 would go in there 3 times. Is that it? Okay, and then you may want to either circle or highlight what you still have left. Okay, multiply across on top, and I've got 4 pi radians. Multiply across on the bottom over 3 seconds. Okay, so 4 pi radians in 3 seconds. So they gave you angular velocity. They asked for angular velocity. All they really wanted you to do is convert units. You do a lot of that in chemistry, don't you? With moles and things. Yeah. Okay. A lot of conversion of units. Okay. Okay. We did angular velocity is omega equals theta over time. This one is linear velocity. Okay. Linear velocity. Okay. Linear velocity is linear distance traveled by a point per unit of time. This goes all the way back to, you've done this before, distance equals rate times time. Okay. The only difference is they're going to put it on a circle. If I was doing angular velocity, I'm really looking at, okay, what's the angle that it maps out per unit of time. But if I'm doing linear velocity, I'm saying what's this distance that it maps out per unit of time, not the angle. Okay. So if I use this, but in trig we're not using d for distance, we're using s. Okay. So if we did s equals r. Actually, let me do this a different way. Let me do it a different way. Solve this for rate. If we were solving this for rate, go distance divided by time equals the rate. Okay, but our distance is s. S divided by t. And we're not using rate, we're using v. Okay? So if you start linear velocity equals the distance, s, divided by t. Okay? But what does s equal? S equals r theta. Okay? So go back. In this formula, substitute in for s. V equals, so s equals r theta, so you can substitute that in. Okay? But what is theta over time? Omega. Okay, so V equals, the main formula for linear velocity is V equals R times omega. This is the main formula for linear velocity. V, linear velocity. V stands for linear velocity. The R stands for the radius. Over here, the R was the rate. And then the omega equals angular velocity. Okay? Same thing on this one. If you're substituting in a radius, to get the units to divide out correctly, it has to be per 1 radian. When you sub in here, it's got to be per 1 radian. Okay, so let's look at an example. say the wheel of a car is turning at 15 RPS, revolutions per second. Find the angular velocity in radians per second. This R is revolutions. Okay. Now this is the same as what we did up above. They're giving us revolutions per second. They're asking for radians per second. So they're still asking for omega. Write the formula down. Omega equals theta over time. They're giving us 15 revolutions per second. We want to convert it to radians per second. It's already in seconds, so that's good. So then we want the revolutions to divide out. So one revolution all the way around once is how many radians? 2 pi. So 2 pi radians. Okay, and then reduce it. The revolutions divide out. Okay, and then multiply. And we end up with 30 pi radians per second. Okay, 30 pi radians per second. I don't care if you write it, you can write it 30 pi radians per second. That's the same thing. Okay. Okay, now this one's going to tie in with the one up above. Okay, with that one. Find the linear velocity of a point 1 foot from the center in feet per second. Okay. So this time they want linear velocity. So V equals R times omega. Okay, so the V, the radius, 1 foot from the center. Okay, so the radius is 1 foot, so it's 1 foot. To get this to divide out right, it's per 1 radian. That's the little trick to that. The omega, you just solved for it up here. Sub that in. 30 pi radians per second. Notice if we had used 15 revolutions, we would not have been able to divide it out. Okay? Now you can divide it out. The radians divide out. Okay? And you have 30 pi feet per second. Okay? Now, think about this for a minute. Does the angular velocity, you can abbreviate it, does the angular velocity change if the radius equals 2 feet? So if I took and mapped out an angle here, okay, if I go out, does the angular velocity change? Wouldn't this map out the same angle as this per unit of time? So the angular velocity does not change. Does the linear velocity change? If the radius is 2 feet? Look at this distance. Isn't this mapping out a longer distance per unit of time than this? Yeah. So the linear velocity changes, but not the angular. Okay? 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 Another example. Find the linear velocity in miles per hour of a point on the rim of a CD whose radius is 2 1/4 inches. That's about the normal size of a CD, like a music CD. Find the linear velocity in miles per hour of a point on the rim of a CD whose radius is 2 1/4 inches if the angular velocity is 35,000 RPMs. Okay, we're finding linear velocity. Okay, so formula V equals R times omega. The R 2 1/4, change that. That would be 9/4, so it would be 9 inches per 4 radians. You could actually put 9/4 on top and 1 on the bottom. That would also work. Okay. The angular velocity, they gave us the angular velocity, 35,000. R, that R is revolutions per minute. The problem is I want it in miles per hour. Okay? Now you got to go through and convert all those units. Okay? Let's do the time first. Okay? So if we do the time, 1 minute. Ooh, no. Sorry, I want the minutes to divide out. 60 minutes in 1 hour. Okay? That would get the minutes to divide out, and we'd be in hours. Now I need to go miles. And all I have is inches. 12 inches in 1 foot. How many feet in a mile? 5,280 feet in 1 mile. Okay, so now we'd have our, okay, but now we have a problem right here. Okay, still got to get that to divide out. Get the revolutions to divide out. 1 revolution is how many radians? 2 pi. See if we got it on. Okay. Now, you can go through the reducing all that. You can also do it on your calculator. If you do this on your calculator, look up here for a minute. If you do it on your calculator, you're going to put in 9 times 35,000 times 60 times 2 pi, put it in parentheses, divided by 4 times 12 times 5,280. Okay, do that. neighbor. Did you end up with about 468.561 miles per hour? Do you understand now why at a certain point inside computers, okay, companies had to say, okay, we've got to build a better CD, otherwise that CD is going to explode, okay? It will blow up, it will shatter inside a computer, okay? Because a point on the outside rim is traveling at 468 miles per hour inside there, okay? Okay.